Hello everybody and welcome back to page 58 of the workbook. In this video we're going to prove Corollary 3 to Lagrange's theorem. Okay, let's take a minute just to read this. This is a very short, simple statement that they're making. It tells us that a group of prime order is cyclic. So this is, when you think about it, kind of a remarkable fact. It's saying that if you have a group and you know that the number of elements in the group is a prime number, then there's only one kind of group that it can be, and that's a cyclic group. There aren't any other possibilities. Okay, and we're going to see if we can use Lagrange's theorem to prove this. All right, so let's start by supposing that we have a group whose order is prime. Okay, and what we're going to do to start our proof off is to choose any element in the group that's not the identity element. Okay, choose A and G. Such that A is not equal to E. Okay, well, if we start with a non-identity element, then that means if we look at the cyclic subgroup generated by A, it's got to have more than just the identity element in it. Okay? The only way that, or said another way, we take the order of that cyclic subgroup, it can't be 1. It's got to be bigger than 1 because we started with a non-identity element. Okay, so we've got that. And we'll add another piece to this sentence that we started here. We also know that the order of that subgroup has to divide G. That's Lagrange's theorem again. Must divide the order of G. And I claim as a result of that, the only other possibility is that the order of the subgroup generated by A is the order of G. Okay, why is that again? Okay, well, what does it mean for a number to be prime? What are the only divisors of a prime number? The divisors are either 1 or the entire number. Okay, and we ruled out the possibility that the order is 1, and so the only other possibility is that the order of this subgroup is equal to the order of the entire group. Okay, so I'm just going to remind you where this statement came from again. This is directly because of the fact that the order of G is prime. Okay, but notice what we've shown here. We've shown that this subgroup, okay, the cyclic subgroup generated by A, has the same number of elements as the entire group. The only possibility then is that this number A is a generator for G. Okay, so G has to be equal to the subgroup generated by A, and by definition, that means that G is cyclic. Okay, and we are done.